Today's math lesson will tell us how to match exponential functions and their graphs. As we begin this process, let's examine the different parts of the parent function for exponentials, being f of x equals a times b to the x power plus c. As we begin this process, we're going to look specifically at a and b. As our graph is pointing off to the right, we need to see, hey, what direction is it coming from and where it's going? And that is based in large part on whether or not a is positive or negative. So if a is a positive number, our curves could be traveling upwards to the right or bottoming out, just kind of flattening out as we travel to the right. If a is a negative number, then as we travel to the right, our curve could be going down, down, down very quickly, or it could be, again, topping out, not so much bottoming out, but topping out as we head to the right. As we look at the b part of our equation for the parent function, we're going to be looking at the graph as it points to the right, and we're going to see how it travels based on the behavior of the number b. If your b number is greater than 1, not equal to 1, just greater than 1, then as your curve travels to the right, it could be pointing upward very quickly, or it could be pointing downward very quickly. Now, this is important to discuss. What does it mean to be greater than 1? So when we say that b has to be greater than 1, we have a big set of variety of what that could be. Now, it might be a huge number, like, I don't know, 374. That's definitely greater than 1. Or it could just barely be greater than 1, like 11/10. That's 1.1. So it's only barely greater than 1, but it's still greater than 1. Our other option for b is to be any number between 0 and 1. So it's not going to be a negative number less than 0. It's just going to be something between 0 and 1. And these curves, as they travel to the right, are either going to bottom out, and they're going to just, as they move to the right, just bottom out, or they're going to top out, flatten out, as again they move to the right. So it's very important as we start at the beginning of exploring these functions, as we want to see what their graphs are going to look like, by analyzing what the a value is and the b value is. And you can quickly say, oh, it has to be one of these red two options or these two blue options. And then you could say, oh, it has to be one of these two green options or one of these two orange options. And then you say, okay, which one do they have in common? And that's how we're going to be processing through these problems as we discuss a and b. Now let's talk about c from our parent function. So c creates a vertical shift, and it is something very important with y equaling c, as this is the horizontal asymptote. So we have a new vocabulary word, asymptote. An asymptote is a boundary. It's like a fence, and it's the height at where this curve is going to flatten out. So our curve is never going to cross the asymptote. It's never going to touch the asymptote. It just kind of flattens out, tops out, bottoms out here at this invisible fence. Let's talk about a plus c. So as with almost every function that you come across, there is some y-intercept that will occur. And in our exponential functions, that will happen. Our y-intercept occurs at a plus c. Now you might say, hey, in my function, in my equation, I don't have a number in the a position. Okay, so if no a value is showing, then we know that a is equal to 1. And if no C is showing, then we know that C is equal to 0. So we can look very quickly on our parent function. Our A value happens right here in front of the parentheses at the very beginning of our equation, and our C value, if it exists, happens at the very end where it is either added or subtracted off at the end of our equation. So after we have discussed what A, B, and C are and how they affect our graph, it is really a great idea to make a very tiny table just to help verify the points that you need. So this table, this little XY table, it can be very small. You might need to test an X value of -1. You should be able to fill in the X value of 0, as this is your Y-intercept that you can get from A plus C. And then you really should test what happens at X equals 1. And you plug this 1 into your equation for the X value, and then you can get an actual value to put in here to make a coordinate point. Now, I recognize that all of these characteristics, all these traits of exponential functions really can be confusing to analyze as you get started. I get that. So if that is proving itself to be too much, although I think you're going to see the patterns of behavior start to happen really very nicely, very quickly, if this is all too much, too confusing, then graph. Graph the equations that they give you on Desmos and start comparing. After you graph it on Desmos, then you need to look at the table. And you're going to look at the table for the values, for the coordinate points of the function there on Desmos so that you can match it up to the appropriate graph of your 4 graph options. So I think you're going to find that the characteristics, the traits of the exponential functions works pretty nicely so that you won't need to go and graph in Desmos. But if you do, that is most definitely an option that always works. Here in example 1, we're going to match each exponential function, g of x, r of x, n of x, and k of x, to its graph. To start this process, I really like to take a moment and just find where all of our y-intercepts are located, and also any clean points, particularly what happens when x is equal to 1. Because those are the points that I encouraged you in the introduction to look at on a table. So we see here in all 4 of these graph options that the y-intercept of each of our graphs is equal to 1. We also see the varying values of what's happening when x is equal to 1. So in our first graph, when x is 1, y is 3. On our second graph, where x is 1, y is 4. On our third graph, where x is 1, y is 2. In our fourth graph, where x is 1, y is 5. So I'm hoping that you're going to quickly begin to see a pattern of behavior given the functions that we have to work with. Our first function to look at is g of x is equal to 2 to the x power. So to get this started, let's look at a. A is the part of our equation that does not have an exponent on it that comes at the very beginning. And we learned in the introduction that if there is no number here in front of the equation that doesn't have an exponent on it, then we know that a is equal to 1. And you have learned from all of your mathematical training that if there is no symbol showing, then we also know that a is equal to a positive 1. So from the introduction, we saw that if a is a positive number, then our graph is going to be moving steeply upward to the right, or possibly just flattening out as we move to the right. So let's look at what b is. b is equal to 2, and b is always the number that has the exponent on it. So here we're looking with b if it is greater than or less than 1. So 2 is obviously greater than 1. And curves with a b that are greater than 1 move to the right either sharply upward or sharply downward. So from this, right now, we can already begin to see what the shape of the graph should be. So we say, what do these two sets of options A and B have in common? Oh, they have this one, this moving sharply upward to the right, which makes sense because all 4 of these graph options have the same style of graph, moving sharply upward as we travel to the right. Now let's talk about C. So C comes at the end of our exponential function, and we said in the introduction, if there is no number added or subtracted at the end, then C is equal to 0. So this is where our horizontal asymptote would be if we were asked to graph it. So we continue this process by now adding A plus C. So my A value was a positive 1. My C value is 0. Why do we do this? Because we saw in the introduction that A plus C is the y-intercept, which 1 plus 0 is 1. Great. So now let's finish this off by looking at, do we have any options? Well, before we do that, let's make our tiny table. So our tiny table of x and y values, really I need the x is equal to 0 and then x is equal to 1. So our y-intercept happens when x is equal to 0, and we saw the y-intercept is 1. And all 4 of these graphs have a y-intercept of 1. So that still stands, but it hasn't really helped narrow things down for us. So let's find out what happens when x is equal to 1 by plugging this 1 into our original equation for the x value. So 2 to the 1 power is just 1, 2, which you can either get by knowing or you can get by putting it into a calculator. So here's where things get to be narrowed down nicely. This coordinate point is currently living at an address of 1, 3. Here we have a coordinate point at 1, 4. Here's a coordinate point at 1, 2. And finally, a coordinate point at 1, 5. So now we know what the height is, what the coordinate point is whenever x is equal to 1. And there it is. There's the one that we need. It's right down here at the bottom. And so we can say that this bottom graph is our g of x, which equals 2 to the x power. Let's analyze our second equation that we need to process. So r of x equals 3 to the x power, again starting with a. So again, if there is no number showing here in front of the number that has an exponent, then we know that a is a 1. And from your previous math learnings, if there's no symbol here, it is a positive 1. And we learned in the introduction that graphs with a positive a value will travel steeply upward to the right, or they're going to kind of bottom out, flatten out as we travel to the right. Our b in this equation is a 3, and 3 is most definitely greater than 1. So again, from the introduction, we know that when b is greater than 1, our graph is going to travel steeply upward to the right, or it's going to travel steeply downward to the right. And just like we did with our previous equation that we analyzed, we say, all right, so a and b have what style of curve in common? Here it is. Steeply upward to the right. And that still matches all of the graphing options that we have. So a good deal. Let's go look at C. So as we said with our first equation, that if there is no number showing adding or subtracting at the end of our equation, then we know that that is a 0. So our C value is 0. And if we were asked for the horizontal asymptote of our graph, we could say C is equal to 0. We use that to find our intercept, our y-intercept, by adding a plus c. So we have 1 plus 0. So again, our y-intercept is equal to 1, which stands to be true for all 4 of our graphing options. So let's finish this off, because we haven't been able to narrow down our search, by making a tiny little table where we've got x values of 0 and 1. So the y-intercept is when x is 0, so that has a value of 1. And then let's plug a 1 in for the x value of our equation. So 3 to the first power is just a 3. And we look at our 4 graphing options and we say, oh yeah, here we are. Here's the only graph that has a coordinate point on its curve of 1, 3 that we saw here in our little table. So that gives me an equation of an exponential function of 3 to the x power. For the purpose of being able to see the writing of analyzing graphs, we're going to analyze in a slightly out of order fashion. So let's look at k of x is equal to 5 to the x power. So again, let's start off with a. So a still is sitting here in front of the 5 as an invisible, understood, assumed positive 1. And we know that that means our curve is going to travel steeply upward to the right, or it's going to flatten out, bottom out as we travel to the right. And b is equal to 5, because it is our number that is a base that has an exponent of x. And 5 is most definitely greater than 1. So its curve travels either steeply upward to the right or steeply downward to the right. And as we've seen before, what a and b have in common is this traveling to the right steeply upward. Okay, so let's continue forward looking for c. So c, still the number at the end of our equation. And again, if nothing is visible there, that means c is equal to 0. And we use that to help us with a horizontal asymptote. Or, well, actually, in addition, we can use it to help us find our y-intercept. So a is 1 and c is 0, which means that our y-intercept is their sum, which is going to be 1. And from there, we can make our little t-chart to help us plot important points. We know that we can graph the y-intercept, which is x is 0, at 1. And then we can figure out, by plugging in 1 for the x value, that 5 to the first power is just 5. So here it is, the graph that shows us a coordinate point of 1, 5. That means that our bottom right graph option has an equation of k of x is equal to 5 to the x power. So reasoning says that the equation we haven't used yet should be the graph that we haven't labeled yet. But we're going to verify that we've actually done the work correctly. So let's do that. So n of x is equal to 4 to the x power. Again, a is equal to a positive 1 because there's no number here in front of our base that does have an exponent. So again, we know that our graph either has to travel steeply upward to the right, or it has to flatten out, bottom out as we travel to the right. And b is equal to 4, because b is for base, you could say that. And it has an exponent, which is definitely greater than 1. So our graph is going to travel steeply upward to the right, or steeply downward to the right. And again, we say what a and b have in common. That same one. So good, that agrees with the graph that we have still available as an answer option. We look at c, and c, because it is not showing in our equation, we know is equal to 0. And we can use that to help us find our y-intercept. Since a is 1 and c is 0, that means that our y-intercept is equal to 1. And finally, let's go make our little table of x and y values. So we know our y-intercept when x is 0 is equal to 1. And let's plug in this 1 into our equation for x, and we get 4 to the first power is equal to 4. And don't you know it? That is exactly what we find in the one graph answer option that we haven't used yet, which is really great to know that we don't have to depend on just the answer we haven't used yet, because we know that we've done it right. And there you go. In example 2, we're going to again match each exponential function, h of x, q of x, j of x, and k of x, to its graph. So I like to get all of these graphs started in their analyzation by looking at where their y-intercepts are located and also what's happening at x equals 1. So sometimes when we have x equals 1, you'll notice this is not a clean coordinate point. So we can kind of take a guess. This is going to be 1 and 1 point something. Not a lot. It's going to be small. I'm going to take a wild guess. No, I'm not even going to take a wild guess. It's going to be 1 point something small. This x equals 1 is going to be something very small. So this will be 1 and something tiny, just above 1. We don't know what exactly. So here I have the point. It is nice and clean where I have 1, 5. So that's really nice to have. And then on my last answer option where x is 1, this is below 1 in height, but it's not a lot below 1. So this one is really tiny, way below 1, almost down to 0. And we can write that here, almost 0. And this is just below 1, and so we can write that, almost 1. Sure, and that just helps us to know what we're doing. And this we can say is just a little bit more than 1. A little more than 1. So that just helps us with some reference points. So let's get started looking at our first exponential function where h of x is equal to the quantity 5/4 to the x power. Okay, so a being the number that is in front of the base, it does not have an exponent on it. We see that it is positive as there is no sign showing. And we saw in the introduction that if there's no number showing, that's a 1. Great. And we know that positive a values are either going to travel steeply upward or flatten out as we travel to the right. Great. B. So b in this particular function is 5/4. Now this, if you don't think in fractions, if you only think in decimals, then you could transfer this into a decimal, and it is 1.25. A quick way to remember that this is greater than 1 as just a fraction is if your numerator is bigger than your denominator, which it is. Okay, so b is 1.25, it's 5/4, and that is definitely greater than 1, which tells us that our curve could either travel steeply upward to the right or steeply downward to the right. And we need to determine what type of curves these a and b numbers have in common. Steeply upward to the right, and that works. So 3 of our 4 graph options give that to us. So up and to the right. Ooh, I lied. Not 3 or 4, 2. So this is flattening out as it goes to the right. I have another steep upward to the right, and then I have a flattening out to the right. So I already know that whatever h of x is, it has to be one of these 2 options here. Okay, so let's keep going. So c, we know, is there at the end of our equation, and since no number is present, or at least visible, we know that c is 0. And from that, we can go find our y-intercept. So a is 1, c is 0, That means that my y-intercept is their sum, which is 1. Let's make our tiny table of x and y values. We have the y-intercept, and then we also have x at 1. So we found that our y-intercept is 1. So both of these two curves have a y-intercept at 1. And then let's plug a 1 in for our x value. So 5/4 to the first power, if you put that into a calculator, or if you just say, hey, 5/4 to the first power is just itself, then we know that 5/4 is equal to 1.25. So that's a little more than 1. And that is exactly how we described this coordinate point here where x is equal to 1. So I know that h of x, where we have the quantity 5/4 to the x power, is the function for our first graph. Our second exponential function, q of x, is equal to the quantity 1/5 to the x power. All right, so let's see what we've got. We know that a is still the number in front of the parentheses, and since nothing is visibly present there, we know from the introduction that's a positive 1, and it is going to travel either upward steeply to the right, or it's going to flatten out, bottom out as it travels to the right. And then b is 1/5. So here my numerator is definitely smaller than my denominator, which means that 1/5 is less than 1. If you think in decimals, then you could say, oh, this is 0.2, if that helps your brain. And we know that these particular graphs are going to travel flattening out, bottoming out to the right, or they are going to top out, again flattening out, but topping out to the right. And we see between my A graphs and my B graph options that this flattening out, bottoming out to the right is what they have in common. So let's see, we know that we have two graphs that look like this. We've got my second graph here as it is flattening out, bottoming out, and I have my fourth graph as it is really rather slow in its movements all the way across anyway. So it's been trying to flatten out for a long time. All right. So now we need to look at C, and as there is nothing added or subtracted at the end of our equation, we know that C has to equal 0, which will in turn help us to find our y-intercept. So 1 plus 0, which means that our y-intercept is equal to 1. And both of these graphs have a y-intercept at 1. So that hasn't narrowed the search at this point. Okay, let's make our tiny little table of x and y, where my y-intercept is at 1, and then when x is equal to 1, we would have 1/5 to the first power. So anything to the first power is just itself. So that's still just 1/5. And that is a tiny little number, like almost 0, tiny little number. So if you needed a decimal value, 1/5 is equal to 0.2. It's 2/10. So almost 0, there that is, up here at the top, that is my descriptor right there, almost 0. And so that means I've got q of x is equal to the quantity of 1/5 to the x power. And we can even label, we can fill in the blank of, hey, that was a 0.2. And while we're at it, we can go back and we can fix this of 1.25. There you go. All right, let's look at j of x, which is the quantity of 4/5 to the x power. Let's see what that does. So let's start off where we always start. A is equal to a positive 1, as it is understood where there is nothing showing before the parentheses that is a positive 1. And we know that means our graph is going to travel steeply upward to the right, or it's going to bottom out and flatten out as we travel to the right. And B is equal to 4/5. So 4/5, my numerator is smaller than my denominator, which means that this is less than 1, but it's pretty close to being equal to 1, as 5 divided by 5 would be 1. So, okay, so this is less than 1, which means that we are going to travel down and to the right as we bottom out, flatten out, or up and to the right, bottoming out, topping out, flattening out. And again, we see what A and B have in common is this flattening out as we move towards the right. Great. So if you needed a decimal value of 4/5 to help your brain understand what that means, you could figure out pretty quickly that 4/5 is equal to 8/10, 0.8. All right, so let's go find C. So again, I have nothing added or subtracted to the end of my equation, so I know that C is equal to 0. And that helps us to find our y-intercept. So A plus C, which is 1 plus 0, and that is my y-intercept equaling 1. Great. Both of these graphs have a y-intercept at 1, so that doesn't narrow anything down. We do think that this is going to be our answer, but we need to verify it because, and I believe this will be our answer because of how this graph is shaped. Coming down, traveling to the right, flattening out, bottoming out, and that is what it does here. All right, so let's verify. So, X and Y table, I have my y-intercept. We're going to look at a value of X to see what happens. My y-intercept is 1, and let's plug in a 1 for this X. So we have 4/5 quantity to the first power. Anything to the first power is itself, 4/5. So at X equals 1, Y has a height of 4/5, which is almost 1. It's 0.8. And that's what we found here. It was almost 1. It's at 0.8, which means that this fourth graphing option is our J of X with the quantity 4/5 to the X power. So our fourth exponential function is K of X is equal to 5 to the X power. And it should, if we've done everything right, be this third graphing option. But let's verify. That's the great thing about math. We don't have to assume. We can and should verify. So, A, there is no number multiplying in front of the 5 that we can see. So we understand that is a positive 1, meaning that our graph travels up and to the right or down, flattening out as it travels to the right. And B is equal to 5, which is very much greater than 1. No guesses there. And when B is greater than 1, then we know it's going to travel up and to the right, or it's going to travel very steeply down and to the right. And we see that what these two, A and B, have in common is this nice steep up and to the right. And that is how our third graph does travel. So that's nice to be able to see that what we're expecting to happen is happening. Let's check on our C. So C is again equal to 0, which helps us find our y-intercept as we add the A value to the C value. And we get an answer, a y-intercept of 1, as it definitely has a y-intercept of 1. And then we go make our little table. So X and Y, I have my intercept, and I have my 1 for the X values. So the y-intercept was 1. Let's plug a 1 in for the X. So 5 to the first power. Any number to the first power is just itself. So that tells me I have a point at 1, 5. And I absolutely do. It's already labeled, which makes it really nice when we can say, hey, everything is in agreement. We have verified that everything that we have works. And there you go. In example 3, we're going to match each of these exponential functions, Q of X, K of X, R of X, and T of X, to its graph. As we begin this process, let's look and see what our graphs have to offer us before we even look at the equations. I'm able to find all 4 of my y-intercepts very easily. 3, 1, 2, and 4. Great. And our x equaling 1 values, let's look at those. So our first x equaling 1 is just below 1. Not by a whole lot, but by something. So below 1. And our second graph shows that we are again below 1, but by a lot more. So this is still below 1, almost 0. In our third graph, we see that x at 1 is again below 1, but it looks very similar to the one right above it. Not identical, but very similar. So it's just below 1. And our fourth graph is nicely on 2. So I don't even have to question really what's happening here. So that's very nice to work with. Our first exponential function reads q of x is equal to 3 times the quantity 1 over 4 to the x power. So A is a genuine 3. That's pretty nifty. And because we have no symbol in front of it, we know it is a positive 3. This tells us that our graph will be traveling upwards to the right, or it will be traveling down and bottoming out to the right. Great. B is 1/4, which is definitely less than 1. And if you need for your brain's sake a decimal value, that's 0.25. So 25/100ths. Yes. And so those graphs where B is less than 1 either travel down, bottoming out to the right, or up and flattening out to the right. There we go. So we see, okay, what do these two A and B value graph types have in common? Aha. So this is going to be a graph that travels down and flattens out to the right, which all 4 of these options are. So we are in agreement right now with what we were given in the pictures. So C is not visible, so we know that we have not added or subtracted any specific value. C is 0. And now let's go find our y-intercept from A plus C. So with A equaling 3 and C equaling 0, that tells us our y-intercept is equal to 3. So right here, I only have one graph with a y-intercept equaling 3. So let's verify that this is our q of x equation by looking at a quick table of x and y values. So our y-intercept 0, 3, and then when x is equal to 1. So if I have 3 times 1/4 to the first power, that ends up being 3 to the 1/4. And 3 times 1/4 is 3/4. There you go, simple fraction multiplication. And if you need a decimal value, that's 0.75. And hey, we said this was going to be below 1, but not horribly below 1. And that's exactly what this is. So great, we found that our first equation of q of x equaling 3 times the quantity 1/4 to the x power is our first graph that they gave to us. Our second exponential function is k of x equals the quantity 1/3 to the x power. Here we go. So A is equal to a positive 1, as there is no visible number in front of the parentheses, telling us that our graph will have to travel steeply upward to the right or down, bottoming out as we travel to the right. And B is equal to 1/3, which is very clearly less than 1. And if you need for your brain a decimal value, that's approximately 0.33, with the 3 repeating. Okay. So that again tells us that our graph is going to come down and bottom out, or it could come up and top out. And we see that between our A and B graph type options, we have this down and flattening out in common, which again is what all 4 of my graph options look like anyways. So that tells us that we're doing something right. Man, isn't it nice to know when you're doing something right? Okay, C. So there's no visible number added or subtracted to the end of our equation, so C is 0. So let's go find our y-intercept of A plus C. So that will be 1 plus 0, telling us that our y-intercept is equal to 1. And here it is. So we only have one graph with a y-intercept equaling 1. That's it. So most likely, that's going to be the graph that we need. Let's go verify. And we'll do that by making a tiny table with x and y values of 0 and 1 for x. So our y-intercept when x is 0 is equal to 1. And our value of x equaling 1, let's plug that in. So 1/3 to the first power, any number in the whole wide world to the first power, is just equal to itself, 1/3. And we know that 1/3 written as a decimal is approximately 0.33, where the 3's repeat. And that is very below 1, almost 0. So that's in agreement with what we thought at the beginning. So that's really nice. And we see that our second graph will be k of x is equal to the quantity 1/3 to the x power. Our third exponential function is r of x is equal to 4 times 1/2 to the x power. So let's go see what happens. So a is the number in front of our parentheses, which is very much a positive 4. Great, nice and visible, easy to work with. So as it travels to the right, we'll either be going upward, nice and steep, or we'll be coming down and flattening out to the right. And b is equal to 1/2, which is most definitely less than 1. And we know from the introduction that b values less than 1 are going to be coming down and flattening out, or coming up and flattening out. And as we've seen before, those two A and B values have a similar type graph coming down and flattening out, as both of our last options remaining are in that style. So that's super. We know that with nothing added or subtracted at the end of our function, that we have a C value equaling 0, which helps us to find our y-intercept as 4 plus 0, telling us that our y-intercept is 4. So between these two graph options, our fourth and final option is the only one that has a y-intercept equaling 4. So this is most likely our correct graph for our r of x equation. Let's go make sure. So if we build our tiny table of x and y values, where I have my y-intercept and x is equaling 1, I know my y-intercept is 4. And let's plug in a 1 into our equation and see what happens. So 4 times 1/2 to the first power. So 1/2 to the first power, well, that's just 1/2. And half of 4, well, that's 2. And that is exactly the coordinate point that we found right here. Nice and easy to work with. So that tells us our fourth available graph is our r of x, which equals 4 times the quantity of 1/2 to the x power. So let's go talk about t of x equals 2 times the quantity 1/3 to the x power. Our third graph is the only one that we haven't named so far with its a personal appropriate exponential function. So it stands to reason that this third graph will be t of x, but let's verify. As always, gotta verify. So let's start with A. A is a positive 2. So our graph will either travel up and to the right steeply or down, flatten out to the right. B is 1/3, which is definitely less than 1. And as we stated earlier, if you need a decimal version, that is 0.33 repeating. And those styles of graphs where b is less than 1 will either come down and flatten out. Oops, that got a little bit more tight in the corner than necessary. Or it'll come up and flatten out. There we are. So we again see an agreement between A and B of the style of curve that we should be expecting, and that is what we see here, and that's helpful. We know that if nothing is added or subtracted visibly at the end of our equation, that C is equal to 0. And then we're going to use that to go and find our y-intercept, where A is 2 and C is 0. So my y-intercept is equal to 2. And it is. So that's really great. That's very helpful to, again, be in agreement with what our graph is and what our equation is telling us. So let's go verify our final one last point with a small t-table of x and y. So I look at x values of 0 and 1. So when x is 0, my y-intercept is 2, which we already found. And then plugging in a 1 for the x, if I have 2 times 1/3 to the first power. So 1/3 to the first power is just 1/3. And 2 times 1/3 is equal to 2/3. And again, if you are in need of a decimal to help your brain, that is 0.66 repeating. And that is basically what we have here. We said it was less than 1, but not catastrophically less than 1. So this is 0.66 with the 6's repeating. And we have our equation of t of x is equal to 2 times 1/3 to the x power. And there you go. In example 4, we're going to match the exponential functions of r of x, s of x, t of x, and v of x to their appropriate graphs. As we begin the process of looking through our 4 graphing options, we first find their 4 unique y-intercepts. So I find here that 2 of my graphs have a y-intercept of 2, while my other 2 graphs have a y-intercept of 3. And we also see that our graphs are pointed in opposite directions when we have this same y-intercept. So that's interesting. The second thing we look at is what's happening when x is equal to 1. So here on our first graph, where x is equal to 1, we see that there's a corresponding y value, a height of 6. That's a nice clean point, so that's nice to work with. On our second graph, where an x is equal to 1, it looks almost as though we have a perfect 1.5. So this looks like it's probably 1.5, and we'll verify what that is as we go through the problem. On our third graph, we have when x is equal to 1, again, we have a perfect height of 6. Very interesting. And here on our fourth graph, again, I have an x value of 1 with a height. This time, now it's below 1. So we're going to write below 1. It's not like catastrophically below 1, but it is 0 point something. So we'll go find out what it is. Our first exponential function is r of x equals 2 times 3 to the x power. So let's get started. So a is very much a positive 2. And because of that, we know our graph is going to travel steeply upward to the right, or it's going to flatten out as we head to the right. And then b is equal to 3. That's our base. And that is very much greater than 1. And we've seen from the intro and previous examples that where b is greater than 1, our graphs can travel up and to the right, nice and steep, or down and to the right, nice and steep. And we see here from our A and B of the different styles, directions of travel of our graphs. We have this nice steep upward movement up and to the right happening. So that tells us I'm either going to work with my first graph here, or I'm going to work with the graph right below it. So both of these graphs have a 1, 6 as possible coordinate points on its path, but we have a y-intercept of 2 versus a y-intercept of 3. So let's go check it out. Looking for c, we know that if nothing is visible, adding or subtracting to the end of our equation, we know that c is equal to 0, and that helps us find our y-intercept by adding a and c together, where a is 2 and c is 0, so therefore my y-intercept is equal to 2. So it is most likely that our first graph will be the appropriate one for our exponential function of r of x. Let's verify that with a quick little t-table where we look at our y-intercept and an x equaling 1. So we saw our y-intercept has a value of 2. And let's go plug in a 1 for the x. Oh, that's right there. So 2 times 3 to the first power. Anything to the first power is itself. So then 2 times 3 is equal to 6. So we do have the coordinate point 1, 6, which is very present, very visible on our given first graph, which is great. So our first graph comes from the function of r of x equaling 2 times 3 to the x power. Our second function to work with is s of x is equal to 2 times 1/3 to the x power. So let's get started. A is a positive 2, so that tells us that we are going to be traveling up and to the right, nice and steep, or coming down and traveling to the right, flattening out. And B has a value of 1/3, which is very much less than 1. And if you need a decimal, that's approximately 0.33 with the 3's repeating. And these graphs are going to be traveling either down and to the right, flattening out, or up and to the right, again, flattening out. So we see here that the two graph styles, these A and B both have this down and to the right, flattening out in common. And that's really helpful because here is my second graph, down and to the right, flattening out, and my fourth graph, down and to the right, flattening out. So it should be one of these two graph options that we choose. So let's look at C. There is nothing visible added to the end of our function. Therefore, C is equal to 0, and we can then determine our y-intercept, where A is 2 plus C, which is 0. So our y-intercept is equal to 2. So our fourth graph option should be the graph that we look for. This should be our match, and we're going to continue verifying that with our little t-table. So here's x and y, with x equaling 0 for the y-intercept, and then we'll check x value of 1. So the y-intercept is 2, which we have here. And let's go plug in a 1 into our function. So 2 times 1/3 to the first power. And 1/3 to the first power, any number to the first power is itself. So 2 times 1/3 is 2/3, which is the same or equivalent to 0.66 with the 6's repeating. 0.66 repeating, or 2/3. And that is about what we said here. We said it was below 1, but not like all the way at the bottom near 0. So that is in agreement with what we saw before we even began dissecting our equations. And as a result, we can say that this fourth graph is the equation of s of x is equal to 2 times the quantity 1/3 to the x power. Oh, and now you can actually see it. Our third function, t of x, is equal to 3 times 2 to the x power, is what we need to analyze now. So let's do that real quick. And we know that a is equal to a very positive 3, telling us that our graph is going to travel up and to the right, nice and steep, or down and flattening out. And b is equal to 2, which is very much greater than 1. And that being said, our graph should travel up and to the right, nice and steep, or it should come down nice and steep. So we see between these two graphing types, we have this up and to the right, nice and steep as what they have in common. And that is very much what we have as our third graphing option. So let's look at this real quick. We have a y-intercept of 3, and truthfully, if you look at the other one, let's move the paper, they both have a y-intercept at 3. So we really need to verify. We need to take a minute to verify what's happening on this t-chart, even though we suspect that we will be traveling up and to the right. So let's go make sure that we know what we're doing. You got to know that you know. So there's nothing added to the end that's visible telling us that our C as a result is 0. And we know that we can find our y-intercept by adding A plus C. So A is 3 and C is 0. And we know, therefore, our y-intercept is equal to 3. But we already knew that had to happen, as that's the only option from our two graphs. So let's go check out our t-table. So x and y. So the y-intercept, we know that's 3. What happens when you plug in a 1? So 3 times 2 to the first power. So 2 to the first power is just 2. So this is really 3 times 2. And 3 times 2 is 6. And there it is, right there. The coordinate point 1, 6, here visible on our t-table. So we had suspected, because of the direction that we discussed, that we believed it would travel, and it does. And then we also verified it with our t-table. So again, it continues to be really, really nice when you have your understandings of the behaviors of curves match what you find in the numbers. So it stands to reason that our fourth exponential function of v of x equaling 3 times the quantity of 1/2 to the x power should be this second graph that we were given to work with. It should. So let's go find out that we really did know what we were talking about. A is equal to a very positive 3. So that means our curve will be traveling up and to the right, nice and steep, or down, flattening out right there. And then B is equal to 1/2, which is very much less than 1. And graphs that are less than 1 will be traveling down, flattening out, or up, flattening out. And we see between A and C that we have this come down and flatten out in common, and that's great. And that does agree with what we have for our second graph option as it comes down and flattens out. So that's nice. Let's keep going. We don't have anything visible adding at the end of our function, so therefore we know that C is equal to 0, and we can determine what our y-intercept is by adding our A value and our C value, and we learned that a y-intercept is actually 3, and it is. So again, we're still in agreement, and it is good to be in agreement. It is great when the facts verify themselves and there's nothing left to speculation. So let's go finish this off with an x and y. We have our y-intercept when x is 0 equaling 3. And let's go find out what happens when x is equal to 1. So 3 times 1/2 to the first power. 1/2 to the first power is just 1/2. So 3 times 1/2 is equal to 3/2. Or if you really are wanting that decimal, that's 1.5. It's not even an approximate. It's right on the nose. So we have right here, we said, hey, this looks like this point crosses right in between a height of 1 and 2. And it does. It does. That's really nice that this makes the 1.5. Our table is in agreement. Therefore, our second graph ends up being what we suspected, a v of x equaling 3 times 1/2 to the x power. And there you go. Here in our fifth and final example, we're going to match our exponential functions to their graphs of g of x, t of x, w of x, and h of x. As is always good practice, before you get started analyzing your equations, analyze your graphs. So we have found our y-intercepts on all 4 of the given graphs, and then we've looked to see what's happening when x is equal to 1 at all 4 of our graphs. So on our first graph, when x is equal to 1, we see our curve all the way up here just above 6. So just above 6. So that'll be helpful to help us just see that we're going in the right direction. In our second graph, we see that our curve lands, like it nails it. When x is 1, it drops down to a -2. We see here on our third graph that when x is 1, we see it's just above a +1. So we don't know where yet, but we know it's close by. It's just right above it. And then on our fourth graph, we see that when x is equal to 1, we again have nailed a coordinate point, and this time at -3. Looking at our first exponential function of g of x, that's equal to 2 times the quantity of 3/5 to the x power plus 5, let's get started. So we see that a is equal to a +2. And that tells us that our graph will be moving to the right, nice and steeply upward, or down and bottoming out, okay? And b is equal to 3/5. Since our numerator is smaller than our denominator, we know that this value is less than 1, telling us that our curve will either be coming down and bottoming out as it travels to the right, or up and just flattening out, topping out as it travels to the right. And we see here that between A and B, we have this style of curve where you come down and flatten out, heading to the right in common. Okay, so that is 3 of the 4 options available to us. So it should be one of those 3. Great. Let's look at C. Hey, look, we actually have a value showing in our equation. So C is equal to 5. Well, that's nice and different. All right. That tells us that we have a flattening out at 5. Okay. Let's see how else can we use this? So for our y-intercept, where a plus c is going to be 2 plus 5, we see that our y-intercept is equal to 7. Okay. So looking at our graphs, right there, I have a y-intercept equal to 7. So this is probably the curve that we're going to be using for our g of x equation. Let's verify with a small table to find out what other things our numbers are doing. So x and y, we have x equaling 0 for our y-intercept at 1. Let's check this out. So 2 times 3/5 to the first power plus 5. Okay, order of operations. So 3/5 to the first power is just 3/5. And 2 times 3/5 is 6/5 plus 5. And 6/5 plus 5, you could rewrite that to be 6/5 plus 25/5, making 31/5. And if you need that decimal, that is 6.2. And hey, don't you know it? That is so very much what we had said in the analyzing of our graphs. We said this was just above a 6, and it is. That's a 6.2 right there. So we see that our first graph is our g of x equaling 2 times the quantity 3/5 times x plus 5. Nice. In our second equation that we have here to analyze, we have t of x equals 5 times the quantity 3/5 to the x power minus 5. Let's go. So a is equal to a positive 5, telling us our graph will either travel up and to the right nice and steep, or down and flatten out to the right. And b is equal to 3/5. So since our numerator is smaller than our denominator, we know this is less than 1. And if you need a decimal value to help your brain, this is 0.6. Yep. And I didn't list that up there in the first part, but that's okay. And so these graphs traveling to the right are going to be down flattening out to the right or up flattening out to the right. And we see here that between A and B, we have this down and flatten out in common. Okay. So what do we have here as an option? So that could be either our second graph or it could be our third graph, just depending on what the numbers tell us. So let's go find out what they say. So C, hey, here again with C, we have an actual visible number in our function, so that's pretty nice. So our C is -5. Let's go use that to help us find our y-intercept. So A is a +5, C is a -5, therefore my y-intercept is going to be 0. Well, isn't that interesting? And there we have a y-intercept of 0 right there on our second graph. Okay, let's go verify that this is the graph that we need. Small t table, x and y. Y-intercept at 0, that gave us a y value at 0. And let's go check out what happens when x is equal to 1. So 5 times 3/5 to the first power minus 5. Order of operations. 3/5 to the first power is just 3/5. So 5 times 3/5 is just 3. And 3 minus 5 is -2. Aha. So, let's see. So my y value when x is equal to 1 is -2, and that is exactly what we see here in the given coordinate point, telling us that our second graph of t of x is equal to 5 times the quantity 3/5 to the x power minus 5. Let's look at our third exponential function. So we have w of x equals 2 times the quantity 3/5 to the x power. So let's see. A is equal to a +2, telling us that our graph will either travel up and to the right nice and sharp, or it'll come down and to the right flattening out nice and sharp. Or let's see, B has a value of 3/5. And that is, again, less than 1. This is still 3/5 is 0.6, telling us that our graphs will either come down and to the right, bottoming out, or up and to the right, topping out. And we see here that A and B have this particular style in common of down and to the right, bottoming out. So most likely, this will be our graph for our w of x. Let's go verify. Let's go find out. So I don't have a c added or subtracted at the end of our equation. That tells us that c is equal to 0. And we know from a plus c that we can find our y-intercept. So our y-intercept is equal to 2 plus 0, which is 2. And hey, that is the y-intercept on our graph. That's helpful. We are again verifying. Let's go look at our table very quickly. So t-table of x and y. So the y-intercept when x is 0, y is 2. And let's see what happens when x is equal to 1. So 2 times 3/5 to the first power. So 3/5 to the first power is just 3/5. 2 times 3/5 is 6/5. And 6/5 is equal to 1.2 if you need that decimal. And we said it was going to be just above 1. So this is a 1.2, verifying that as we had suspected, Our third graph is our w of x, where 2 times 3/5 to the x power is its function rule. So here we are at the end of our fifth example, where we only have h of x equaling -5. Ooh, that's different. Times the quantity 3/5 to the x power. To work with, we assume it's going to be this fourth graph that we don't have a label for yet. But let's go verify to make sure that we know what we know. Okay. So here we see that a is actually a negative number. A is a -5. This is different from all the examples that we've done so far today. Since this a is a negative number, that tells us our graph is either going to go down and to the right very steeply, or it's going to come up and flatten out as it heads to the right. Okay, that's different. And b is still 3/5, which is still less than 1. And so we know from that our graph will either come down and flatten out to the right, or it will come up and flatten out to the right. And we see between A and B, the style of graph they have in common is this come up and flatten out to the right, which is exactly what we see here in this graph. So that's very nice that we have things that are in agreement already. C. So there's nothing visibly added or subtracted at the end of our equation, telling us that C then must be 0. And we can use that to help us find our y-intercept, as A is -5 and C is 0. As a result, our y-intercept is -5. And that is what we see right there in that graph. So again, it's really nice to see, hey, our numbers are matching what we had suspected in our analyzing of the graph. So let's make our t-chart to just bring it home. We've got x is 0 and its corresponding y value is -5. Let's find out what happens when x is equal to 1. So -5 times 3/5 to the first power. So 3/5 to the first power is just 3/5. -5 times 3/5 is equal to a -3. Yep. And that is exactly what we have in this coordinate point. So again, it matches. That's really nice. So we see our fourth and final graph is our suspected h of x is equal to -5 times the quantity 3/5 to the x power. And there you go.